All right, so collisions. We mean one object running into another, or even a couple objects running into each other. In any problem involving a collision between objects, momentum must be conserved. Oops. Specifically for the collision itself. So when we say the initial momentum of the system must equal the final momentum of the system, we're talking that the immediately before the objects hit each other and immediately after. So very, very tiny time frame of the collision itself. So for any system at all, if we have two objects that are going to collide, and not a spring, not one box and a spring, this, we would use energy. If we had more than one box and a spring, we would technically use momentum. So when I'm saying two objects, I mean like two cars, or playing pool, the cue ball hitting another ball to try to sink it in a pocket. A football player tackling another football player. That's what I mean by two objects. The momentum of object 1 plus the momentum of object 2, both of them immediately before they run into each other, must still add up to the same value right after they run into each other. Since momentum is mass times velocity, we can write this as m1 v1 initial plus m2 v2 initial. Oops. m1 v1 final plus m2 v2 final. Again, velocity, so we have to account for directions, which we'll be doing some examples, but just keep that in mind. Vectors matter. This conservation of momentum is true for all collisions. This can be used for all collisions involving two objects. It also can be used for all explosions. And that term is used very lightly. We don't mean blowing something up. Just something that somehow, say, the football player isn't close enough to tackle, so they reach out and push on this guy and make him move. That would be considered an explosion. For a split second, the guy's hands on the shoulder of the other player, that push gets the player moving more so in the other direction, so they came apart. That could also be a collision. Anyway, explosions, we mean anything that just breaks apart somehow. It's very mild as far as we are concerned. Keep this in mind though. Anything that looks like a collision or explosion, just jump to this concept of conservation of momentum. There are technically two types of collisions though. Collisions can be broken into two types. One type is called elastic collision. The other type is called inelastic collision. A subset of inelastic is called perfect inelastic, or completely, something along those lines. Different wording can be used. But that perfect inelastic collision is still inelastic. It just has a specific meaning. In perfectly inelastic, the definition of this is that the objects stick together. This could technically be a football player tackling another one, but they're not letting go, so they fall to the ground at the same time together. It could be throwing a ball of clay or putty at something and it sticks. So some sort of situation where the objects stick together when all's said and done. Problems have to specify that either they stick together or that it is perfectly inelastic. All that means is when we're thinking about the final momentum and saying P1 final plus P2 final, well, if they're stuck together, these velocities are the same. So V1 final is the same as V2 final. So we can just call that a V final. We would be able to say M1 plus M2 together are traveling at this same V final. That's what's special about perfectly inelastic collisions. Now, the general definition between elastic collisions and inelastic collisions is how we can talk about energy. With elastic collisions, we can say that the kinetic energy, 1/2 mv squared, the kinetic energy of the system as a whole prior to the collision, it doesn't change form. It's still kinetic energy, finally. No thermal energy is generated. No other form is created in that small time frame of the collision itself. So not only is momentum conserved, like we've already said, but also we can write out saying that 1/2 m1 v1 squared initially, if we add up the kinetic energy of these objects, that total kinetic energy, I don't know why I'm writing it in the opposite order, sorry. That total energy is still there, finally. Now, it will change. Object 2 might finally have more kinetic energy than object 1, but it will still be kinetic energy. That's the definition of elastic collision. This was true for objects that don't change shape overall, like a racquetball hitting a wall. The racquetball looks the same after as it did before. I mean, technically it can break in the process if you're hitting it hard enough. But in the normal play, assuming the racquetball looks the same as it leaves as it did when it hit the wall, that is considered elastic. Okay, bowling, a bowling ball hitting a pin can be approximated as elastic. The bowling ball is still this nice sphere, the pin is still the same shape. Technically, a little bit of energy is sound because we hear the collision, but it's so small and insignificant that we don't really need to account for it in that situation. On a molecular scale, collisions between atoms are elastic. In Inelastic simply means some of the kinetic energy of the system turns into thermal energy or even other types of energy that are not kinetic or potential. For example, if a car rear ends another car, typically there's a dent. Or even worse, it could be worse. It takes energy to cause a dent in a bumper or to break off your lights that shatters. So ultimately, if the objects, or even one of them, look different at all and stay looking different after the collision, it took energy to make that happen. It takes energy to make a dent in the bumper of a car. It takes energy to take the bumper all the way off a car. And so some of the kinetic energy the system has before the collision is other forms of energy that are not kinetic. That's what we mean by inelastic. The energy does not stay in the form of kinetic energy after the collision. So we could technically just say K initial of the system does not equal K final of the system. Typically, using conservation of energy is not useful if the collision is inelastic, because we don't have enough information to calculate this energy up front, usually. But the beauty is, momentum up here, momentum is conserved in any type of collision. Any and all collisions. So my go-to, if I know I'm dealing with a collision, and the problem is wanting me to relate somehow the speeds to each other, or velocities, I start with momentum. And then if I don't have enough information, I go and look at what other information the problem has given me. So momentum, conserved in any collision, which is very nice. We will go through some examples so that we can see you do have one part in the test notes. Let's see if this will copy over. Awesome. This statement in this momentum chapter, these two equations are right below the section that talks about inelastic and elastic collisions. Now, because in elastic collisions, let's see, both this momentum and kinetic energy are conserved, for elastic collisions, we often get a system of equations to solve. Our author has solved one situation for us, and that's what this statement is for. This tells you specifics about the situation. So solving the system of equations for an elastic collision. That means both conservation of momentum and conservation of energy. These equations can only be used, number one, if you know it's elastic, you know you only have two particles. This concept, moving only in one direction, means everything happens along the same line. So like a car's not a particle, of course, but a car hitting another car, any motion has to take place along the same line. So even if you play pool or billiards, if you hit the cue ball and it hits another ball on the edge, the other ball will take off at an angle, as will the cue ball. This is not one direction. So here, when it says moving only in one direction, we have to know the two particles or objects that we are approximating in this elastic collision, that all motion will happen along that one line. The other qualification is the first particle is starting with an initial velocity, and the second one is at rest. The reason this is so specific is when we think about conserving momentum, which is totally conserved even if this is not the situation. Momentum is conserved simply because it is a collision. But remember, vectors, we can only add x components of vectors together to get x component vectors. So when we are solving problems involving collisions, we're going to have to break each problem into x and y, just like we did with projectile motion, just like we did with forces. By specifying in only one direction, we're saying the velocities are all either completely x direction or y. So in my picture, this one I drew to the right, there would be no momentum in the y direction, neither before or after. That's what they mean. And so this momentum equation, the v initials and v finals are just these x velocities. So we would use a positive sign for something moving to the right, a negative sign for something moving to the left. So that just simplifies the momentum into one direction. The second one at rest means there is no V2 initial. And then, since it's elastic, there's going to be no, well, I'll write it out. Kinetic energy is conserved because of the definition of elastic collisions. So ultimately, these are the two equations they are solving to get these two answers. V1 final is the final velocity of the object that was moving initially, right? Remember it says the first starting V1 initial. So V1 final means the velocity of that first particle that was moving. V2 final is the final velocity of the one that was at rest to begin with. And it's nice, if we know our problem fits this situation, don't solve this system of equations, because it's already been done for us. If your problem doesn't fit this situation, do not use these equations that come from the test notes. So these are very specific, the ones that I copied and pasted in here. They are specific to this situation. So don't try to use them for every problem. Now, a couple interesting things. V2 final is always going to be in the same direction as V1 initial. So if my initial particle is moving to the right, V2, the second object after the collision, will automatically be moving to the right. But the first one, the one that was moving initially, could potentially end up moving to the left. And that's based off of that numerator. We end up with the difference in their masses. So if M2, the one that was at rest initially, If that mass is bigger than M1, object 1 will bounce off and move left after the collision. If M1 is the bigger one, object 1 continues to the right. It slows down, but it continues in the same direction it was in to begin with. And one other interesting, what if M1 was equal to M2? Well, M1 minus M2 would give us 0. That would result in object 1 literally stopping and object 2 continuing on. So some interesting situations in this specific case. We will go ahead and do I'm going to do a number of example problems that will help show you how to approach different problems. So practice with those, but again, make sure if you know you have a problem, involves a couple of objects colliding, just start with momentum and go from there.